Hello my dear students and welcome once again to Zenith Academy Online. Today we are doing part 2 of the chapter Sound, where we will be talking about sound waves. So this is the introduction of sound waves. Let's start. So what is sound? Sound is nothing but energy. Okay. So sound is a type of energy in the form of which waves? I explained you in the last class about mechanical waves. So sound is a type of energy in the form of mechanical waves that produces a sensation of hearing in our ears. So I'll just recap what are mechanical waves. Those waves which require a material medium for their propagation or for traveling ahead. Okay. So sound requires air to pass. So when I'm talking, there has to be a medium, air, then only the recorder is going to record my voice, or if you are sitting in front of me, then you are able to hear my voice because there is air in between us. Okay. So the medium can be air, that is gas, liquid or solid. Okay, if there is a medium, then only it will travel. So sound is a type of energy in the form of mechanical waves that produces a sensation of hearing in our ears. We are able to hear. Okay. Now, how is sound produced? How is it produced? It is produced by vibration of a body. And what it requires for the propagation? It requires a material medium for its propagation. So two things are very important. So if you are asked how is sound produced, what is the condition necessary for production of sound? Okay, for production of sound, what is the condition necessary? Tell me. The condition necessary for production of sound is vibration of the sound producing body. And what is the condition required for propagation or its traveling or its motion? Propagation. What is the condition required for its propagation? The presence of material medium. Material medium, what do you mean? A medium which you can touch, that is solid, liquid or gas. Okay. So for production of sound, vibration is important. For propagation of sound, material medium is important. Okay. Now, so a sound wave is a pattern of disturbance and it is caused by the movement of energy traveling through a medium. So what travels? Basically the energy travels, nothing else. The particles do not travel. The particle just vibrate about its mean position. So a sound wave is a pattern of disturbance caused by the movement of energy traveling through a medium as it propagates away from the source of sound. So energy propagates from the sound wave propagates from the source and reaches the listener. Okay. Now, many a times we have this doubt that sound waves are longitudinal or transverse. Okay, sound waves are like this, okay, or like this. So sound waves basically are longitudinal waves in solid, inside a liquid and in gas. So if you take a glass, if you take a jar, fill it with water, okay, and you place a timer or an alarm inside, you are able to hear, when you are standing out here, you are able to hear the ringing of this alarm because sound can travel through water, sound can travel through this solid, and then sound can travel through air. Okay, it is traveling through water, then solid, the container, and through air, and you are able to listen. So sound travels in solid, inside a liquid and in gas. Okay, and in that case it is longitudinal. I have already explained you what is longitudinal, where the wave particles vibrate like this around the mean position and the direction of propagation is also like this. So they are in the same phase. But my dear students, sound is also transverse. Okay, sound can propagate as transverse waves but only in solid and on surface of liquid, not inside the liquid. Inside the liquid it travels like this, longitudinal, but it can also be transverse only in solids and on surface of liquid. So sound waves are both longitudinal and transverse, but most of the sound wave are longitudinal. Transverse is only on the surface of the liquid or sometimes in the solid when it is transferring on the upper layer of the solid. Okay. So you cannot say that sound waves are only longitudinal. Sound waves are longitudinal in solid, inside a liquid and in gas. You have to use inside a liquid, because on the layer of liquid, on the surface of liquid, it is transverse. Okay. So if you take a water body and produce some high pitch sound, you can see the water vibrating in this form. Okay. So that is transverse. And when inside the liquid, so it is on the surface of the liquid, it will be like this, but inside sound will travel like this, rarefaction, compression. So if you are listening through the sound, see, if this is the beaker. Okay, so if you are listening, you are able to listen, it is because of longitudinal wave, because inside it is traveling as longitudinal, and above if you see the ripples on the water surface due to sound, it is because of transverse. Okay, now let's talk about the speed of sound. So sound travels with a finite speed in a medium and takes time to reach our ears. So when I am speaking and if there is someone standing here, then his ears, the sound will take some amount of time to reach him. Okay, so from the source of production, it will take some time to reach the ears. So speed of the longitudinal wave depends on two factors. Okay, first factor is elasticity of the medium, and second factor is the density of the medium. Elasticity is given by capital A, density is given by rho, Greek letter rho. Okay, so velocity of the sound is square root of elasticity upon density. Okay, so you can say here that velocity is directly proportional to square root of elasticity and velocity is inversely proportional to square root of density. So as the elasticity increases, velocity also increases. As the density increases, the velocity decreases. Okay, so let's talk about the relation. So relation of speed with elasticity. Just now I said कि speed is directly proportional to square root of elasticity, right? So elasticity is related to the tendency of the material to maintain shape and not deform. So what is elasticity? Elasticity is the tendency of the material to maintain its shape and do not get deformed. So whenever a force or stress is applied on it. So in general, if you know that solids are very strong, solids do not change their shape, they do not get deformed. So we say solids have the strongest elasticity, then liquid and then gas, and that is the reason the longitudinal sound waves travel faster in solids than they do in liquids and gas. So the speed is highest in solids, the velocity is highest in solids, okay, then in liquids and then in gases. So you must be knowing this. Your teacher or someone must have told you that when you have to listen to some sound. So sound travel high with the maximum speed in solids. So for example, the railway tracks, when you want to listen the approaching train coming, so the sound that travels through air and reach your ears will take time. But when you keep your ears on that solid railway tracks, you can feel the vibration, you can listen to the sound earlier. Because what happens, one more thing, in the solid the particles are very close to each other. So when this particle is vibrating, it is able to transfer the energy here very quickly, whereas in liquids they are little far off, so it takes time to transfer the energy. And sound is nothing but energy. One particle vibrate and pass its energy to the next particle, then that vibrate, pass its energy to the next, right? So in solids these are anyways very close. So sound travels fastest in solids because the elasticity is highest. Okay, velocity is directly proportional to square root of elasticity. Now what about density of the gas or density of the medium? So speed of sound is inversely proportional to the square root of the density of gas. Lighter the gas through which the sound passes, greater will be the speed of the sound. है ना. So if the gas is lighter, less dense, the sound will pass with high speed. Okay, so the speed of the sound in gas increases with the increase in the temperature of the gas. Obviously when you increase the temperature, okay, the density will decrease, and if the density decreases, the velocity will be more. So that is why speed of sound increases with the increase in temperature. This happens because increase in temperature, the density of the gas decreases. Now, the speed of sound also depends on humidity in air, the presence of moisture in air. So remember, speed of sound also increases with increase in humidity in air, because there is now in between the air particles, now there are water particles also, so it becomes easy to transfer energy like this, right? So speed of sound in gas is now independent of, so it does not depend on pressure, wavelength, frequency and amplitude, है ना. It does not depend on pressure, it does not depend on pressure, it does not depend on wavelength, does not depend on frequency and does not depend on amplitude. It depends only on humidity, it depends on temperature, it depends on density and it depends on elasticity. Okay, please remember this. Now let's differentiate between light waves and sound waves. We have already done few of the differences. I have already told you that sound waves are mechanical and light waves are non-mechanical in our last video. So let's talk about this. So light waves are electromagnetic waves, that is non-mechanical in nature. They do not require a material medium for their propagation. Do you remember? That is why they can travel in vacuum. Whereas sound waves, these are mechanical or elastic waves and this cannot travel in vacuum. It requires a material medium for the propagation. So these are the two main differences. Then light waves are transverse waves, whereas sound waves we just studied can be transverse as well as longitudinal. Now the speed of light waves in air is 3 into 10 raised to power 8 meter per second. So high, 3 into 10 raised to power 8 meter per second means 1, 2, 3, 4, 5, 6, 7, 8. So many zeros are there, meter per second. And the speed of sound waves in air, sound wave ki speed is 330 meter per second. 330 meter per second. So it is less. That is why when there is lightning, okay, we are able to see the light first, because light travels faster, and then we are able to hear the sound, the thundering sound later on. Now the light waves, the frequency of the visible light waves is in the range of 3.75 into 10 raised to power 14 to 7.5 into 10 raised to power 14 hertz. Okay, hertz is the unit of frequency, frequency, which is equal to 1 by time, and the unit of frequency is hertz. Now the frequency of audible sound, the sound that we are able to hear, is 20 to 20,000 hertz only. Okay, 20 hertz to 20,000 hertz we are able to listen. Okay, we are able to hear that sound. So that are the major differences between light waves and sound waves. Now let's talk about the propagation of sound waves. How does the sound wave travel? We have understood how sound wave is produced by the vibration of particles. Now how it travels? We just now did, it requires a material medium. So what is the condition necessary for propagation of sound? The condition necessary for propagation of sound is the presence of the material medium, like solid, liquid or gas. The medium has to be there, it cannot be vacuum. So let's see here. In air, the sound propagates as longitudinal waves that comprises compressions and rarefactions. And in this chapter, most of the time we'll be talking about the propagation of sound through air. So we'll be talking always about this type, longitudinal waves. We'll talk about longitudinal waves. But to understand the characters of waves, we will compare it with transverse, right? So now what is happening when I am speaking? Okay, listen to me very carefully. In the next class, I'll show you this also. Tuning fork also I will show you in the next class. Today I forgot to bring it with me. Okay, so what happens when I'm speaking? I'm saying something. So even if when you hit, so there's a vibration in my throat, in my vocal cords, there's a vibration. So I pass that vibration in the air that is around my mouth. Here, the air that is there, I transfer the vibration. So when this tuning fork is vibrating, okay, what will happen if I make a dotted line? It will be like this in the first phase, then it will, the vibration will be inside, so it will be like this. So when it is vibrating out, so what it is doing, this is pushing the air. So the air becomes dense here. Can you see? The air becomes dense here. So there's a compression created. Okay. Now this compressed air will pass its energy. So it will relax. Now the second word when I say, again I am passing the compression. So there's a compression, then relaxation, rarefaction. It goes ahead. Compression, rarefaction, compression, rarefaction, compression and rarefaction. So this way sound waves travel ahead. Okay, so when I'm speaking, the sound wave is contracting. Okay, the particles become close to each other. Okay, a pause, again the air expands, again I'm speaking. Okay, so when I'm vibrating, in the second one I'm going inside, my tuning fork prangs are going inside, so the air gets time to expand. Then again I'm doing like this, again I'm expanding, so again compression. So there's this wave of compression and rarefaction created. Okay, so there is a pressure variation. If you see here, there is a lot of pressure. The volume is less, pressure is more, density is more. Okay, so this can be compared with, the compression can be compared with crest. Can you see crest? And the rarefaction can be compared with trough. Okay. So, a compression is that part of a longitudinal wave in which the particles of the medium are closer to one another than they normally are. So, can you see the particles are closer? And there is a momentary reduction in the volume of the medium. So, for a moment there is a reduction in volume. This is less, you can see this is more. Or a temporary increase in density, or we can say a temporary increase in density. You can see the particles are so close to each other here. So compression is the region of high pressure, you should understand. Okay, compression is a region of, so when I am talking about compression, the pressure is high, the density is high, but what is low? Volume. It is covering less area, na? You can see volume is low. So if you see here, these are drawn by lines. Actually they are not lines, the real picture is this. But for the ease of drawing, this is how we draw the pressure variations. Now a rarefaction. What is a rarefaction? A rarefaction is that part of the longitudinal wave in which the particles of the medium are farther apart than the normal. The particles are farther apart, very dur, okay, than normal. And there is a temporary increase in the volume. You can see there is an increase in the volume, or a temporary decrease in the density. Increase in volume or decrease in the density. Now they are farther apart, the particles. So rarefaction is a region of low pressure. I hope this is clear, compression and rarefaction. Now these compressions and rarefaction carry the disturbance with a definite velocity depending on the nature of the medium. So they carry the disturbance, and disturbance is nothing but the vibration or the energy. So when the energy is carried forward by the help of compression and rarefaction with a definite velocity depending on the medium. Just now we knew that velocity is directly proportional to the elasticity of the medium and velocity is inversely proportional to the density of the medium, square root of the density and square root of the elasticity, correct? So the velocity depends on what? The velocity depends on the medium, but what carries? The compression and rarefactions carry this disturbance with a definite velocity depending on the nature of the medium. So this is how sound waves actually travel. The rarefaction can be compared with this, the compression can be compared with crest, and this is the wavelength, the distance between two consecutive compressions or the distance between two consecutive rarefaction. This distance is known as a wavelength. Okay, so here you can see this is the wavelength. the distance between two crests or distance between two troughs. So now in the next lecture we'll come up with, I'll explain you the reflection of sound waves. We'll talk in detail about echo. What are the conditions for the formation of an echo? What are the conditions for hearing an echo properly? The use of echo to determine the speed of sound in air, and also we'll do lots and lots of applications of echo. So stay tuned to Zenith Academy Online. I would like to say that these are the books that I use. I'll just show you. So these are the books that I use for my physics, ICSE Certificate Physics for class 10 by Oswal Gurukul. You can check them online. I'll give you the link in the description, and this is a very amazing book. This book you should actually buy for your preparation of exam. This is the most likely ICSE question bank. So chapters anyways I will explain you, okay, but question bank you will require. This carries category wise and chapter wise questions. So every category questions has been covered. So here the word of advice, the chapter at a glance, short answers, long answer, figure based question, long answers, short numericals and long numericals. Everything has been covered. All the previous year's questions are also there, and it is strictly based on the latest syllabus prescribed by the council. So you can go ahead and have a copy of this. I'll give you the buy link in the description box as well. So keep on learning on Zenith Academy Online. If you like this video, do give it a like, share it with your friends, and do not forget to tap on the bell icon and subscribe to our channel. Bye bye my dear students.